99.99, 99.999, but you cannot buy 100.00, because even the high technology metallurgists know that you always have impurity atoms. But we were fortunate enough, we were able to get rid of all the iron, all the silicate, all the aluminum, and then he says, Dave, there is no absorption or emission spectra in the sample that agrees with any standards we have here at Cornell University. And I said, wait a minute. Aren't you the man that said you could analyze down to 3 to 5 parts per billion? I don't want to know parts per billion. I have 100% something, and I want to know what that is. And he just said, Dave, I can't help you. I don't know what it is. So I came back to Arizona, and we were doing some metallurgical studies with it. We found out that when we melted it with lead, it would settle to the bottom of lead. So it had a specific gravity, it was heavier than lead. And yet when we brought it into the lead and we put it on a bone ash cupel, which is what they use in metallurgy, the bone ash cupel absorbs all the lead and leaves a little bead of gold and silver. I said, well, let's put it on the cupel and cupel it down. Well, when we cupel it down, there was nothing left. So it wasn't gold and silver. But then we actually took known amounts of gold and we put it in our solution and we repeatedly evaporated that and we cupelled that down and we got no gold or silver. So we weren't able to recover even the gold we put into it. Then I took solutions containing this, whatever it was, and I put known amounts of gold in the solution and repeatedly evaporated it down over and over and over. And then I took that solution up, we extracted it with MIBK, set it into atomic absorption, and it now contains no gold or silver. And then I put gold in it. So I asked the commercial laboratory doing the AA analysis, I said, doesn't this bother you? You know, is it of concern to you that we took this amount of gold, we put it into this solution, we now have it extracted into MIBK, it's a colored solution, we feed it in the AA and it doesn't read. Doesn't that bother you? And they said, not at all. They said, we're running a procedure that was given to us when we bought this machine. It's the standard in the industry, and that's what we're being paid to report. And I said, but doesn't it bother you that it's not accurate? And they said, not at all. They said, in fact, Dave, we don't even have to allow you in our laboratory, and so would you please leave? Now, the gentleman back at Cornell University had also said, Dave, if you'll give us $350,000, we'll put some graduate students to studying it. And I decided for $350,000, I can figure out more than you can figure out. And I don't know anything. So anyway, about 1979, I went to this Siegfried, who was a German fellow with a spectroscopy machine in Phoenix, and he had actually worked for about 27 years in emission spectroscopy. He was the senior equipment designer with Lab Test Industries. He actually engineered and blueprinted and designed emission spectroscopic equipment, and then he went out in the field and set them up and made them work for specialty orders that came into Lab Test down in LA. And when he retired from the company, he had designed and built a 3.5-meter machine. And this is a huge machine. For most of you who are familiar with emission spectroscopy, most machines that are in the universities are about 1.5 meters, and this one was 3.5 meters, which means the arc was huge, you know, that the light is projected on when it does the diffraction experiment. And the great thing about a 3.5-meter emission spectroscopy machine is it really separates the line spectra when it goes through the machine. And so I went to him and I told him that I would like for him to run these procedures that were in the Soviet book that I had been given by the metallurgist. And he said, well, Dave, this is all worthless information you're bringing me because, see, we Germans are the best metallurgists. And he said, I studied over in Dortmund, West Germany, and the West Germans are far ahead of the rest of the world in metallurgy. And this isn't necessary to do the kind of burn time the Soviet book says. He says 15 seconds is the longest burn time you need to run on a sample. That's the standard in the industry. And when you understand that the temperature in the DC arc is 5,500 degrees centigrade. Now that's basically the temperature of the sun. And he says when you put an element on here and strike the arc, in the first 15 seconds, everything there boils away. And he says you read it as it boils away. You actually read it in the DC arc. And that light goes to the prisms, is broken up into the spectra, and you find out which elements are there. He says, so Dave, you know, the Russian book says you burn it for 300 seconds. He says, this is preposterous. In 15 seconds we get everything. And I said, well, this is the Soviet Academy of Sciences, the Vernadsky Institute for Precious Metal Research, a government-funded laboratory that says burn it for 300 seconds. So just do me a favor, and let's just spend my money and burn it for 300 seconds. And so he said, okay, Dave, you know, so he sent to West Germany, had all the orifices built to do the spectroscopic analysis, and you actually have to put an inert gas around the carbon electrode so when you strike the arc, air doesn't get the electrode and oxidize the carbon. And so he said, Dave, we'll burn it for 300 seconds, but he said, this is absolutely worthless. It's just throwing your money down the drain. And I said, well, throw my money down the drain. I have to see it. Well, when he set this machine up and did it the way the Soviet Academy of Sciences said, he struck the arc, and in the first 15 seconds, we read iron, silica, aluminum, traces of calcium, traces of titanium, and that was it. Nothing else. But you look in while that arc is still burning, and sitting there on the electrode is a glowing white ball of material. And it's still sitting there on top of the electrode. And the arc's just going all around it, and it's just sitting there, nothing reading. And it doesn't read for 20 seconds, it doesn't read for 25 seconds, it doesn't read for 30 seconds, it doesn't read for 35 seconds, it doesn't read for 40 seconds, 45 seconds, 50 seconds, 55 seconds, 60 seconds, 65 seconds, and then at 70 seconds, exactly when the Soviet Academy of Sciences book said it would read, palladium begins to read. And then platinum, and then ruthenium, and then rhodium, and then iridium, and then osmium. They actually read in the sequence of their boiling temperatures, exactly as the Soviet Academy of Sciences said they would read. Now, you know, the guy just says, my gosh, Dave, get out of my lab. And he actually sent me away while he reproduced this work for about 3.5 weeks, all on his own. And he called him back up, and actually he didn't call, his wife called me up. And she says, Dave, Siegfried wants me to call and apologize. Now Siegfried, you know, German eagle, he couldn't call me and apologize for himself. He had his wife call him. Anyway, he ran this material over and over and over, and he checked every spectral line. He wanted to be absolutely certain with this material. He checked every possible interference. And he says, Dave, it's these elements. It is these elements. Well, I came back and worked with him about 2 years after that, and we actually worked with this and worked with it until we actually had standards that exactly equaled our unknown material. Now, one of the things that really perplexed us about this material is when we buy standards of rhodium and iridium and ruthenium, we put them on the electrodes and we strike the arc, they read. And they read for the first 15 seconds and then they stop reading. But if you look it on the electrode, there's a glowing white ball of metal. And it doesn't read from 15 seconds until 70 seconds. There's nothing reading at all. And then at 70 seconds it begins to read again. And it reads palladium, platinum, ruthenium, rhodium, iridium, and osmium in exactly the same ratio. And in fact, 85% of the metal read in the late burn time, not in the early burn time. Only about 15% was reading in the early burn time. And so all the commercial spectroscopists in this country who are actually working with these elements are reporting to you 15% of the sample and telling you it's 100%. But it's not. There's a whole bunch more than this there. So I decided, well, look, this is all well and good, but I'm spending lots of money. I got about $70,000, $80,000 in this thing now with all the time and effort and standards and PK blenders and buffers and, you know, over and over and over running this, paying him for all this time for all these years. I said, look, let's just cut to the chase. Let's go right where all the best analysis we can get in this country. What is the very best analysis available at any price?